Okay, so we'd like to begin our opening plenary, and I will introduce our first set of speakers. We have co-speakers for our first presentation. I'll introduce each of them. Barry Nalebuff is the Milton Steinbach Professor at Yale School of Medicine, where he teaches negotiation, innovation, strategy, and game theory. As a graduate of MIT, a Rhodes Scholar and Junior Fellow at Harvard Society of Fellows, Nalebuff earned his doctorate at Oxford University. Practicing what he preaches, in 1998, Barry, together with his former student Seth Goldman, co-founded Honest Tea, now part of Coca-Cola. And more relevant to today's presentation, he advised the NBA in their prior negotiations with the National Basketball Players Association. His co-presenter is Matthew Doria. He's an associate vice president in the salary cap management group at the NBA, where for the past 6 years he's focused on strategy analytics related to the NBA's collective bargaining agreement. Prior to the NBA, Matthew worked for the Siegel Group as a consultant and fully credentialed actuary, where he developed programs and systems to assist sports leagues in evaluating game officials. He received his Bachelor in Science in Mathematics from Boston College and an MBA from NYU Stern School. Please welcome Barry Nalebuff and Matthew Doria.
Thank you for that. So today we're going to talk a little bit about competitive balance in sports. And when we say competitive balance, what we're talking about is the distribution of opportunity among teams in a given league. Now, there's a lot of different ways to think about that and potentially measure it. But two that we find instructive are what we call static balance and dynamic balance. By static balance, what we mean is balance within a given season. Concepts like how close is a typical game, or how many teams have a meaningful chance of winning a championship. Then we have dynamic balance, which we look season to season. Is there a real opportunity for a team to improve from one year to the next, or do the same teams tend to stay at the top? We think both of those aspects of competitive balance are important. For the purposes of our talk today, we're focused only on the static side. So why is competitive balance important? Well, leagues and teams are selling competition to fans, and to the extent there's no balance, we're going to diminish we're not going to have excitement in the product that we're creating. So competitive balance drives excitement, drives appreciation in the product. We know that leagues take competitive balance seriously because they do several things to try to foster it. 3 of our 4 major North American leagues have salary caps, and 2 of our 4 major leagues have luxury taxes. Both of those are tools that are designed in part to prevent teams from gaining excess advantage by outspending their opponents. All 4 of our leagues have rookie drafts that award the best picks to the worst performing teams, and one of our leagues, the NFL, even designs its schedule so that the better teams in one year have a harder schedule in the next year. So if competitive balance is important and it's something that leagues are focused on, there ought to be a good way to measure it. And here we have a very abbreviated history of things that people have done in that area. So back in 1988, Roger Knoll thought about competitive balance as the difference in winning percentage between the best team and the worst team. The main problem with that approach is that it's a little too focused on the extremes. Does the existence of one very bad team really ruin competitive balance for the whole league? So picking up on that, Gerald Scully in 1989 looked at the variance across all winning percentages of the teams. So that was a little better, but one problem that we have with this approach is that we can't compare across leagues using variance because all things equal, the longer a league season is, the less variance it will exhibit because we'll have less variance due to noise. So picking up on that, in 1992, Cork and Fort proposed a metric where we would take the actual standard deviation in the league and to adjust for season length, divide by what they called the ideal standard deviation. That's the standard deviation you would expect if every team in the league had the same ability such that every game was effectively a coin flip. That metric became widely known as the Knoll-Scully metric, and it's been widely used to make cross-league comparisons in what's purported to be a season-length neutral basis. The problem with Knoll-Scully is that it actually doesn't correctly normalize for season length, and that's going to be one of the jumping off points for the rest of our talk. What we actually see is that Knoll-Scully, rather than clarifying the picture of team-level balance, it actually distorts it. And so our goals today are to look at the Knoll-Scully metric, propose a correction, and then take a step back and ask ourselves if we're really solving the right problem. Is team-level variance really what we want to be looking at in terms of competitive balance? That'll lead us into a discussion of game-level competitive balance, and then finally we'll come all the way back around to full season-level competitive balance. With that, I'll hand it off to Barry.
Thank you. So we start off, and I'm an economist, and what I do is, therefore, I take models. And so we have a model for how teams compete with each other, and the simplest model you could do is that each team has a constant chance of winning a game. We'll call that PI. And if I knew the PIs, then I could go and calculate the variance without too much difficulty. But I don't, so instead I have the observed win rates, WI. But to calculate the variance of the WIs, which what I'll notice is the fact that I could take WI minus PI, add the PI compared to a half. The nice thing is I know that in every contest, in every league, in every season, the average team wins half the time. So I know the mean, and I can calculate the variance, and the cross terms cancel, go to 0, because the expectation of WI is always PI. And so that when you go and calculate the expectation of the observed variance, it's just a combination of the statistical noise, the sample size variance, plus the true variance. And for the statisticians in the room, what you might have said is it's the mean squared error is sample size plus bias, but this is the unusual case where we actually care about the bias. That's what we're trying to estimate. That is, if we knew the PIs, we'd be done, but we don't. We see the WIs, and so we have to figure out how to get rid of the sample size error. Okay? What Knoll-Scully does is that they divide the observed variance by the ideal variance, so they divide it by a quarter over n, and when you do that, what you discover is that the first term, the sum of the PIs over n, divided by a quarter over n, well, when you do that, the n's disappear. And so that's great. That term doesn't depend on how many games there are in a season. On the other hand, to the extent that the PIs are not all a half, you have the true variance times n. And so therefore, as the season length goes larger and larger, the term you actually care about is going off to infinity, and so the expectation of this ratio is going to just blow up as the season length gets longer. And by the way, this thing works just perfectly if you assumed all the PIs were a half, but because then the variance in the true variance is 0. But that's exactly the case we don't care about. We're trying to figure out what the variance is when the teams have different abilities. And this thing really matters, as Owens and Kings have shown in their simulations. And if you go from a season length of 16 to one of 82 to 162, so from football to basketball to baseball, the expected size of the Knoll-Scully ratio is going to go up by a factor of 7. Okay, so you can't really use that to make comparisons. So how do you do this instead? Well, one thing you could do is you could say, since the observed variance is sample size plus truth, truth is observed minus sample size, and we could just approximate sample size by the ideal number. So instead of dividing, you subtract. And that's actually not a bad approach, but we could do it exactly right. So let's start again with its observed minus sample size. We know what sample size is if you know the p's. The problem is I don't know the p's. However, there's a neat trick, which is that pi times 1 minus pi is just a quarter minus pi minus a half squared. Okay? And therefore, if I substitute that relationship in, what I discover is that I can change sample size into a quarter over n plus 1 over n times the true variance. And then when I move terms around, what I find is that the best estimate, or an unbiased estimate of the true variance, is just n over n minus 1, so the Bessel correction, times the observed variance minus the ideal variance. And so this is a formula you could use that correctly adjusts for season length, and therefore you can use it to compare variances across different leagues which have different season lengths. And when you do that, what you discover is our intuition changes. Many of the sports commentators have said the NBA is in trouble because its competitive balance is so much worse than all the other leagues. How do they possibly survive? But when you do the correct number, what you discover is the NFL, which people thought is the gold standard in terms of having the least balance, actually is basically the same as the NBA. Baseball, which looked like it was somewhere in the middle, goes to the best because they were being penalized for having a 162-game season. Okay. Now, there are some problems with that model I just presented. One is that I gave every team a constant chance of winning, but if two teams with 60% chance of winning meet each other, they can't both have a 60% chance of winning. So we should fix that. I didn't take into account home court advantages. That changes things. And I also didn't take into account the fact that when one team wins, the other team must lose. It turns out that that third factor doesn't affect how we calculate variance, because we're not calculating the difference between PI and PJ, we're calculating the difference between PI and a half, and summing that up. And the covariance between different teams doesn't change the different PIs. So we are going to go and correct the PIs, and we're going to talk about a little bit how do you correct for home team advantage. So you could, if you had infinite amount of data, try and have a model-free approach where you just estimate PIJ, the chance that team I beats team J, for every possible combination. And I'm sure people in this room will figure out how to do that. An approach that's more commonly used, and we have, I guess, Mark has done this, Lopez, Matthews, and Balmer have done this, where you estimate a strength for each team. And then the chance that team I beats team J is team I's strength over I's strength plus J's strength. And that's great, and that takes, however, 29 or t minus 1 variables you have to estimate. And I wanted to see how far we could go with just one variable. And so the simplest possible model is that the chance that team I beats team J is team I's rank minus team J's rank times delta plus a half. So essentially, the closer teams are into rank, the closer their chance is of winning is a half, and the farther apart they are, and that's all determined by this single parameter delta. So that's nice because I only have to estimate one thing. I'm going to skip some steps here, but just like I showed you how to estimate the true variance in a model where all teams have the constant p, now what I do is instead of saying pi 1 minus pi is a quarter minus pi minus a half squared, I could do pij times 1 minus pij, do that same trick as a quarter minus pij minus a half squared. And when I do that, I get almost the identical formula. So instead of n over n minus 1, it's n over n minus 2 plus 2 over t. And if t is 2, you get the same answer. But essentially, when t is large, because you have about 30 teams, instead of doing a Bessel correction of n over n minus 1, you do n over n minus 2. And I'm not going to show you the graphs because, except for the NFL, it makes almost no difference whatsoever at the size the t's we're at. Having said that, it's not clear we've really been solving the right problem all along, which is we've been focusing on this idea of how much variability there is in the team's success rates, their winning rates. But excitement is going to be much more based on game-level closeness than season-level closeness, if you'd like. And you can see that really at the extreme, which is if we take a model that Fort and Quirk talked about or Horowitz talked about, where you rank teams from 1 to t, and the higher-ranked team always beats the next team, then you could have a team which has a 63% chance of winning going against a 60% chance, and that game is not going to be exciting because the better team always wins. And in fact, in that model, you can see that the variance in team performance is about a 1/12. That's because essentially team records are going to be uniformly distributed over 0, 1. But at the game level, Pij is going to be 1 for one team, 0 for the other. And so the variance at the game level is always going to be 1/4. Okay. What that also says is that variance at the game level is roughly, in this case, 3 times variance at the team level. So what we want to do is then go ahead and calculate game level variance in this simple delta model. Well, I'm going to start by doing that and showing you how to do team level version, and then do the game level version. If we knew the P's, it isn't that hard. I'm sorry, if I knew delta, then I know all the P's. I can calculate, based on the delta, what all the PI's are. I calculate then the PI's minus a half. That turns out to be just some summations of i's and I squareds and constants. And when I do that, I get that the true variance is just delta squared times t squared over 12, approximately. And that's about right if you thought about the fact that delta is 1 over t, which would give you like a uniform distribution, then you'd get that the variance is about a 12th. I can do something similar for the case of variance at the game level, where again, I substitute in for pij minus a half, just I minus j times delta. Now I have to do a little bit more summations because I have I squareds, j squareds, I times j's. And when I do that, I get delta squared over 6 times something that looks like t squared. And here's the neat part of this, which is that the variance at the game level is almost exactly twice the variance at the team level. And why that's useful for me is that, therefore, I don't have to look at every possible game combination. If I know what the variance is at the team level, I'm done, because I can just multiply it by this factor and get variance at the game level. And we already calculated what the variance at the game level was in terms of how to use the observed variance to translate that back into game level variance, to team level variance. So with that, here are some of our estimates that we have that the sigma at the for MLB and NHL is roughly 6%. You multiply that by the square root of 2. You do a little bit of correction for the number of teams, and you get about 8.5% of sigmas for baseball and hockey. You see that there is greater dispersion in terms of basketball and football. They're about the same at around 15% for their sigmas at the team level, and about 21%, 20.5% at the game level. You also see that soccer is somewhere between the two. We can do this, we can also go and use our estimates of our estimates of sigma squared to flip it and figure out what the implied deltas are. So that is, we have one estimate of sigma squared based on the data. We have another estimate of sigma squared based on knowing delta. And so I put those things together, I can figure out what my expected delta is from my estimate of sigma squared. And when I do that, essentially, it's the estimate on the all the way. Where did that go? Oh, here we go. It's my estimate of the sigma squared with the corrections, and that will then give me the delta squared. Love using that little thing. So what we have is our estimate of deltas, which is, I think, really the easiest thing to interpret. One team better in baseball or hockey gives you an extra 0.7% chance of beating somebody. And one team better in terms of rank gives you a 1.6 or 1.7% chance increase of winning in football or in basketball. And to go a little bit further in terms of interpreting that, you can say, where's the best team? In terms of the team with the highest rank, those teams are winning 60% of their games in baseball and hockey, and they're winning 76, 77% of their games in basketball and football. To go one level more extreme, you can say, what happens when the best teams go against the worst teams? And so in baseball, even the worst team has a 30+% chance of beating the best team. In hockey, it's about the same. But in football, when the Patriots play Miami, it's predictable, and it was predicted. So there are going to be a lot of games in basketball and football where you can really know ahead of time what's going to happen. Another way of looking at this is asking, what is the chance that the higher ranked team wins? This is a great statistic that Lopez, Matthews, and Ballmer came up with. And they are estimates here. So for a random game, you're going to have one team is going to have a higher rank than the other. In baseball and hockey, it's about 57% for the higher-ranked team winning. In basketball and football, it's more like 67%. What's interesting is if you compare our estimates to those of Lopez, Matthews, and Palmer, they have fantastic data using betting on every game. They put in all sorts of complicated home team advantages. And if you use the median of their estimates, you can see that our model with one parameter basically comes up with the same numbers. It allows you to differentiate the different leagues. The one place that's a little bit different is in football. And the main reason for that, we think, is that the betting numbers at the beginning of the season don't yet have all the differentiation because you haven't necessarily learned how different the teams are. We're using numbers at the end of the season where you really do know what the quality of each team is. And the beginning of the season plays a bigger weight in football because the season is so short. Okay? With that, let me go back to Matt, because we think that as good as the statistics are in terms of game level variance, there's something that's even more interesting.
So Barry just walked us through in great detail how to kind of take season length out of the equation to calculate team balance and game balance. But one thing that occurs to us is that when a lot of people think about competitive balance in a season, what they're really thinking about is how many teams actually have a chance to finish in first place or win a championship. And it turns out that if that's how you're thinking about competitive balance, you really need to focus on season length and you really need to bring it back into the equation. And so what we do here is we take our team balance estimates and we run them through a simulation model using the actual season lengths. And you end up seeing a picture that looks like this. Here we have a representative season for each of the 4 leagues, and we're showing the top 15 teams ranked on the x-axis by intrinsic ability. On the y-axis, we show the % chance that a team at a certain ability rank finishes the season in first place. So, for example, the best team in the NBA has over a 40% chance of finishing in first, whereas the best team in the other 3 leagues are more in the 20 to 25% range. If we run that down, we see there are 7 teams in the NBA that have a 1% or better chance of finishing in first. That number's 10 for the MLB and 13 for both the NFL and the NHL. So this just kind of, and then if we want to do a league-to-league comparison, we could look at just the NBA and the NFL, which Barry showed us have very close team-to-team and game-to-game balance. But as we play those balance numbers out over many more games in the NBA season, 82 versus 16, we see that it's much more likely for the best teams to rise to the top. So this just goes to show you that if you're thinking about competitive balance in terms of the ability to compete throughout the season, you really do need to bring season length back into the picture. So that's our last point for today, and we hope we've raised some interesting points that you guys have found interesting, and we're happy to open it up to any questions.
We have a few minutes for questions. Any questions? And if you do, we need to mic you because this is all going on videotape for posterity. Can we take this though? Yeah, either way.
Well, I'll say that people have often said that on any given Sunday is sort of the motto for football. But what we've discovered is that perhaps actually that should go for some other sports more than for football.
Yeah, I just have a question. I'm curious. So you said best team. Do you do a playoff simulation, or is best team just measured by the team with the best record at the end of the season?
So it's on a model basis. Let's go back to it. It's on a model basis, so it's more like the idea of the team that intrinsically is the best may not actually end up the best at the end of the year, right? There's randomness that comes from playing, not a non-infinite number of games. And what we're saying is the team that actually has the best ability in the NBA has a 40% chance of actually ending up at the top of the standings. Now, you could also run this through like a postseason model, which we haven't done here, but.
So what we've said is we've done 10 million seasons, and we have our delta model. And if you think that delta is the correct model and it's 0.7 for MLB and it's 1.7% for the NBA, Then you say, well, okay, we know what the best team's chance of winning each game is when they go against everybody else. We know what the second best team's chance is. And so we've made hypothetical leagues for a given delta and then asked for the team with the highest rank, what's their chance that they'll end up at the top of the season. And as Matt pointed out, guess what? You could do the same technique and estimate the chance of winning the playoff. You could ask the chance of getting into the playoff. So once you have your deltas, you can simulate anything you want.
Have you ever considered doing this for college sports like football and basketball and what that might uncover?
Matter of fact, last night I think Barry brought that up. We haven't looked at it, but there's nothing that prevents us from turning this model onto that.
Stay tuned.
I just wondered, if you're trying to estimate PIJs, is like implied money line odds a good approach, or is there another approach?
You could use.
You want to ask the question one more time?
I can say it.
Okay, good.
Can you use moneyline odds to estimate the PIJs? And that would be another way of doing it. And in fact, that is what Lopez, Matthews, and Balmer have done. And we're using ex post numbers as opposed to contemporaneous numbers to do it. But there'd be no reason not to. That's just another way of estimating a delta, if you'd like.
All right, let's thank our speakers once more.